Okay, so this talks about tracking huge files with Git LFS. So I'll give you a bit of background story to this one. So like many great stories, this one starts in Paris. This was a Git merge last year, 2015, really good meetup. And so the day before Git merge, traditionally there's been a Git contributor mini summit, which basically consists of people who've contributed to Git or have a strong interest in it. Basically go off to and have dinner, some talks, and have dinner together later, discussing the future and roadmap of Git development. So at this dinner and drinks afterwards, Git help people and Atlassian, particularly Bitbucket-related people, start talking. So despite what our professional rivalry, we're actually on the down at the bottom. We're actually kind of quite friendly. In fact, while this was happening, I was out drinking with some of the GitHub guys as well. So Nicola Paolucci, who's actually here and is talking tomorrow, and John Garcia were having a chat to Rick Olson, who's one of the major contributors to GitHub. And the conversation went a little bit like this. So Atlassian goes, hey, do you want to hear what we're talking about tomorrow? It's supposed to be a bit of a secret, but we're all kind of hanging out together. As so you'll see it tomorrow. We're giving a talk just before you, and it's really quite exciting. As you know, large objects are a bit of a problem in the Git world. Some people have tried to fix it before; it never quite worked out. We're giving it a go. We're gonna, talking to Go, we're actually writing it in Go. Turns out a lot of previous technologies didn't really work out. Go was a good compromise for us. And we're announcing it tomorrow at Git merge, just after the 10-year anniversary of Git itself. Oh, says Rick, that's a bit of a coincidence, because right after you, we're announcing a project to do large object support. And we've kind of written it in Go as well, and we're announcing it right after you, after the 10-year anniversary. Okie dokie. Right, so what are we going to do about this? What would you call yours? Oh, ours is called Git Lob for large objects. What's yours? Git LFS, large file support. Oh, great. So yeah, basically, two sides have come up to almost exactly the same solution, down to 3-letter acronyms as each other. There were some pros and cons to each side, but we actually kind of had a proper discussion about it. We're all adults. And in the end, it was decided that the Atlassian solution has some technical advantages, but the Git LFS solution from GitHub has a slightly better front-end support, and they had first-mover advantage. We had a working beta internally. They actually had something they were rolling out the next day. So we decided not to split the community. We had enough of that in the world. Let's work together on something. So we actually are actively contributing. The whole thing is actually open source, and it's MIT licensed, and is open to contributions. And both sides and many others, including Microsoft, are actually working on this together. So without further ado, this is tracking huge files with Git LFS, which is the best-of-breed solution we think at this time. And it's gaining some momentum in the community and amongst tool support, which I'll come to in the end. So, quick agenda for this. I'm covering quite a lot, so I want to rush through a bit at the end. But we'll start from the bottom. We'll start a bit about how Git works and about why this is a problem for Git. Then we'll talk a bit about our solution, or the joint solution that we've come up with. And then we'll talk about some practical issues, like how do you deal with an existing repository, and some tips for teams, because it's not about, if you're working by yourself, none of this really matters. It's only really working when you're working in teams, this becomes a large-scale problem. So without further ado, Git data model. Now this is, I would call, an intermediate to advanced talk, in the sense that I'm kind of assuming you know Git pretty well at this time. I am going to do a deep dive right now into Git internals. Hopefully you know most of this already. This will just be a refresher. So the way Git works, it's actually objects. It's all just blobs of binary data that is compressed and hashed down the bottom layer, and everything on top of that is really abstractions. We tend to join these blobs together in certain patterns. We assume that they're going forward over time, or something that looks a bit like time. And then the latest one is what we are generally looking at. So each commit points back at the previous commit, and the previous commit and previous commit. So it has concept of parents, kind of like a linked list going back in time. Each of those is hashed, which means it's actually technically a Merkle tree in the sense that each commit encodes information about its entire history. So if you change history, you have to change the future as well. And on top of that, we build a couple of other abstractions using references to point to things and give them meaningful names. In some ways, it actually looks an awful lot like the Java world. We have even things like GC, but we won't go into that today. I actually do a talk. If this is is new to you or you're interested in the implications of some of this, I actually do a talk that's available on Atlassian's YouTube channel about the implications of this and how to use this knowledge to manipulate and get out of trouble in the Git world. But let's drill down a bit, because obviously this isn't all one giant blob of changes. The changes are broken down into smaller pieces down at the blob level. So each commit will generally is just a bunch of metadata that's stored as a binary object. Now, at the low level, Git has a number of powerful commands for manipulating down at this blob level. And one of them is cat file. That will basically take a hash number or a reference, and with the -p, that means pretty print, just make a best effort to spit it out in a meaningful human readable form. So let's have a look at one of these commits. So this is what a commit is at its simplest form. You have the parent, so where you point back to. You have a bunch of other metadata, committer and author, which is not necessarily the same thing, the commit message, but most importantly, there is the tree. There's a special type of object that is the tree, which is in itself metadata. So let's have a look at that. What the tree is something that looks an awful lot like a Unix file system, because obviously this was written originally by a Unix file system guy. It contains some stuff like the file mode, primarily executable bit is the one of interest here. It tells you a little bit about the type, which is of interest. So trees can point to other trees, which of course makes it a recursive directory structure. Or it can point to blobs, which are themselves traditionally have been text files, although they can be anything. It doesn't really differentiate between text and non-text at this level. Only at higher level, like merges and so on, do we think about things in terms of text. So this is what it tends to look like. We have a bunch of objects and trees. The objects are just binary data, compressed, hashed, but that's all. But the trees may in turn point to other trees, which point to more blobs, till eventually you run out of trees. So classic recursive directory structure. Now the trick here is, as you move forward over time, generally speaking, if you change one bit inside a text file, or any file in the Unix world, in the Git world, you will basically create a new hash. But if you don't modify it, you don't create a new hash. And this is what a content addressable file system means. It means that we address or point to objects by their contents, not their names or anything like that. If it has the same hash, it's the same object, and we can reuse it in multiple places, in particular in other trees. Now, this is where things become a bit of a problem when you start talking about large files. Text files compress well. They're generally not very big, rarely more than a few kilobytes, unless you've got some horrible God class. So this is fine. The other thing is that they tend to merge quite well because we have semantic information about them. However, in the large file world, things get a little bit more complicated. Say we have a tree and it points to an image. This case of an elephant's arse. Quite why it's an elephant's arse, I don't know. I didn't choose this particular image, but we're going to use it anyway and make jokes about it along the way. So it's 50 megabyte image of an elephant. And we've gone, right, cool, okay, nice elephant, but, it should be pink because I was out drinking last night and, you see pink elephants when you're drinking. So it's 100 megabytes. Even though maybe only a couple of bits change. If this was a GIF and you're using a palette lookup to specify the color, that might be nothing more than a few bits of change. But it is now a completely new object. You've now doubled the size of that history in the repository. And we go, well, this drunk elephant, he's had a bit of a big one. He's getting a tattoo on his ass. So we now have 150 megabytes of data in here. No, that's not too bad, because if we're working locally and by ourselves, this space is cheap. The problem is when you're working as a team, which is where Git's real power comes through. So this developer, they've finished their elephant, and they've pushed it up onto the Git repository. then the rest of the team go, cool, let's do a pull. What happens is 150 megabytes comes down, even though they're probably only interested in the latest version of the image. This is the problem with large files in Git, and this is where Git LFS comes in. So let's have a look at how Git LFS solves this problem. It has a bunch of standard, a bunch of extensions to the Git system. In fact, it hooks in, it doesn't actually modify core Git, it actually hooks in some key hook points inside the Git model, or the Git workflow, and I'll talk about those as we go. But what it does, essentially, is where a large file exists, it replaces it with a pointer, some metadata about that file. And then rather than storing that in the Git repository, it stores it in a special store. That gives a lot of extensibility down the line. So what happens when we do a Git push, two operations occur rather than one. Our binaries go off to the special Git store, and the pointers all go off to the standard Git repository. What this means from the point of view of the team is now when I do a pull, a different set of rules kick in. We can have a hook into the system where we can define our own rules. The main rule being we don't always pull out the latest. We pull out everything. We pull out the latest only. So when we do a pull, we only pull down the latest version that we care about. And we can even tune that, and I'll talk about tuning further on. This means that we are going to save a lot of time for a lot of our team. To go back down to the low level, let's have a poke around and see how things work under the hood. Our old friend cat file again. Let's have a look at one of these pointers. So this is actually very simple. It's nothing more than a handful of bytes, which is why it's so fast to store. It contains a version tag. That is nothing more to give us a bit of extensibility, a bit of a wiggle room for the future if we decide to change things. We have an object ID. This looks almost exactly like a normal Git hash. With one change, we're using SHA-256. That's because SHA-1 has shown to be problematic over the 10 years since Git was incepted. SHA-1 is now considered less than secure. SHA-256 is considered best practice now. And we store the size, although that's not super important. It's really just for purposes of caching, if anything else. How do we use this in practice? Let's jump forward a little bit. So you just want to quit here and leave. This is how you get started. You install Git LFS. This example uses Brew because Atlassian is a bit of a Mac place, but there are binaries for Windows and there are binaries for all of the Linux distributions. So you go to Git LFS homepage, you'll see all where to get binaries from. One of the advantages of Go is that it is much more cross-platform than the C that core Git is written in. Then you do a one-time operation, Git LFS install. That will, on your machine, will set up Git LFS in perpetuity. It does that by modifying your global Git config. It adds a filter, Git LFS. And that says we're going to hook into two places. There's a clean filter. We're going to say, when I add a file to a repository, I want you to run this special command before you do it. And that's what the clean filter does. As part of adding a file, it will perform certain operations. Smudge is the opposite. On checkout of taking a binary version and turning it into a working copy, I want you to do the opposite. That is the main hook point. There is one more. Then, for any repository, this is per repository now, we can say git LFS track and tell it the rule. We wanted to make sure that all of our MP4 videos are stored as large files, special case, store them on a special server, treat them as pointers, cut out all the waste. All it does is modify Git attributes. That says for MP4 files, treat them as LFS files. What is actually going on disk is text. And that's all it says. Very, very simple indeed. How this works in practice is this. So our developer goes git add of our massive video. It's a dancing elephant, which we'll come back to. So at this point, our LFS filter kicks in, our clean filter. It runs Git LFS, which does a couple of things. One, it writes out the object as a hash, same as it would do in a normal file, but in a different place, Git LFS objects. It separates them out from the normal Git repository. And in its place, it puts the tag file there, the pointer. And that's pretty much it. At that point, and that goes into your standard Git repository section. So we've replaced an object with a pointer, but put the object to one side and kept it safe. At the other end, what happens is fairly obvious. You do a git checkout. You say, I want to take a revision in history and turn it into a working file. Well, a smudge filter kicks in. At this point, we pull from the objects. Or, and this is important, if it's not in our local object cache, we fetch it from the upstream server. We'll talk more about the upstream server in a bit as well. But that's basically it. And that turns it into a binary file on disk. There's one other hook we hook into, and this happens on a per repository basis, but the Git smudge and clean filters do this for you. How many people are aware of the Git hooks tools? All right, they're pretty cool. The first one, for instance, is if we have a rule that says if you create a commit message, it must always contain the branch name, and we use that in Jira to kick off some cool things, and in Bamboo. So you can write a little script that says always put the branch name in the commit. But we've got one here called pre-push. That's the one that Git LFS has added, and it will do it automatically. You don't need to worry about this. What that does is when you go to do a push, it will kick in before the push is completed. And what that will do is upload any outstanding large files to the upstream large file storage. Only then, once we've uploaded it, do we upload all the pointers as well. Obviously, pretty much the opposite happens when we do a pull. There's no special requirements there. We do a pull, that pulls down all of our pointers, and then when we try and convert our pull into a checkout, which is what happens, a pull is a fetch and a checkout effectively, we then do it, the smudge filter will kick in, and that will then download the latest version of the file if necessary. This also works under SSH as well. Now, I'm going to skip a little bit here. There's some really cool technology about how that works with SSH. Large files currently can only be stored on HTTP servers. But if you're using SSH, you need to go off and find out, well, where is that actual server? Well, what happens here, when I go to a git clone, I pull down all my pack files, and then we try and convert it into a working copy. At that point, the smudge filter kicks in. At that point, we go off to our server. Now, this is where you do need a Git server that is at least vaguely LFS aware, and it must know where the other server is. So I say, I need this particular object with this hash. And then it comes back with a JSON metadata that basically says, it's over there, here's where it is. And there's some really cool stuff going on there as well. It actually will provide authentication keys. So you can get a short-term JWT authentication key that will then allow you to log into that server without any additional work. So then it goes off and says, get me that binary, and it returns it. Now, there is a slight problem here. Now, what happens here is a slightly lower level is when we say, tell me where these objects are, it happens at the smudge filter level. And that happens for every object. Now, if you've got maybe dozens or hundreds of binary files, it's going to run that smudge filter repeatedly, and then it's going to go and create a new connection off on the server. And this can be very inefficient. It's very inefficient in the Windows world because Windows is very bad at forking new processes, and it can be a huge overhead. So, as of Git LFS 1.2, useful tip here, you can do a special type of clone. You can say, I know that this particular thing I'm about to clone is actually an LFS-aware repository. Therefore, I'm going to use Git LFS clone. That does a couple of interesting things. The main one being, it skips the smudge filter and does it all in a single process rather than processing it for each file. It basically pre-processes your smudge filter for you. It also means that it will go off to the server and create only a single HTTP, or more likely a HTTPS connection. They can be quite slow to set up, particularly on low latency, high latency connections. So it only does that once and then batches up and downloads all the files necessary in one big connection, which is a pretty good efficiency hack. Now, this isn't necessary, but it does speed things up, particularly if you are on Windows. So that's some of the work that's actually happening actively, and it's rolled out a few weeks ago. So that's the theory. Let's get into a little bit of practice. You've got an existing system, an existing repository with a whole bunch of binaries in them. You're going, hey, this Git LFS sounds great. Let's convert to that, and we'll save ourselves a ton of time. And you will, though, over time, but not straight away. Because what happens is, Git LFS does not itself convert your repository into a Git LFS repository, or at least not its history. All your history will still be hanging around, and you'll still have, every time you do a clone, all those hundreds of revisions that you did before you did that one revision that's in Git LFS will still be hanging around in your repository. You need to go back and you need to change history. So, how do we do that? Well, the classic way is git filter branch. How many people have used that? A couple, yeah. Generally speaking, it's good that you haven't, because generally speaking, you use this when you screwed up. There's one way you can do this, is you can go back and destroy all the history of those old files. If you don't care about the history, you only really care about the latest one, that's fine. But generally speaking, you put them into revision for a reason. You want to keep the history, so you probably don't want to do this. This will just delete all previous versions of that file. Probably not what you want. Now, a guy called Andy Neff, who's a core Git LFS committer, has written a better version of this, which is a truly epic piece of Unix scripting. This will go through, convert all of your history using filter branch, and then go through and clean up the previous versions, etc., etc. I don't want to understand this. I don't want to. It is exceedingly powerful. It is also something you probably don't want to do. One, it's very easy to get wrong. Two, it's very hard to repeat, and you're probably going to do it over and over again, because cleaning up repositories is something that rarely works the first time. And it's going to be very, very slow, because this is forking processes like crazy. And this does not work when you've got a lot of history. It's going to be very, very slow. But that's okay. We are hardly the first people to come across this problem. In particular, a guy called Roberto Tiley, who works for The Guardian, I believe, a British newspaper. He had this problem. Apparently, I can only assume a lot of people were putting a lot of bad stuff into their Git repository quite a lot, because apparently he was having to go off and clean Git repositories all the time. So he had enough of this, and it was really slowing him down. So he built something on top of JGit. The problem with Git core is there's lots of small binaries you run lots and lots. But when you've got a big, long-running operation to do, it's better to have a single process that works across your entire history all at once. And this is where the BFG repo cleaner comes in. It was built to kill history, but obviously, if you're going to go back and be able to manipulate history, it's kind of useful to be able to do other interesting things as well. The cool thing about it is because it runs as a single process and operates on the entire history all at once rather than chaining lots of operations together, it's 10 to 720 times faster depending on your operations. And because filter branch has more than one usage of just killing history, it's kind of grown a bit, and as of version 1.12.5, but I think that's a few revisions ago, it now has Git LFS support directly. It understands how to convert repositories into Git LFS. So rather than doing this, you can now do this. Install BFG, and then convert to Git LFS and give it a file path, or a file pattern. Very, very useful. There's one little gotcha here. This is all in the documentations, particularly for the release in question. But the way the BFG cleaner works, it kind of assumes you've gone back and, oh, I should have done that, removed whatever you did, and then went, oh, shit, it's in history. And you go back and you go and clean history. So your latest version is correct. In the case of converting to Git LFS, that's probably not the case. You probably want to convert the whole history, so you say convert the whole thing rather than saving the latest version of it. Not super important, just be aware that you should do no blob protection, because that will then do a proper conversion for you. However, that assumes you know where the problem lies, where your big files are. If they're all MP4s, yeah, that's great. But sometimes it's not as simple as that. Some you might have PNGs in there, some are tiny, and there's a few really big ones. You may be talking about a legacy source tree you've picked up, and you have no idea where it's big, but you have no idea where. Like the current set of files are quite small. Someone in history shoved large files in there, taken them out, but the history still exists, so it's in there. So what do? Well, for some reason it's a newspaper. It always seems to happen in newspapers. A guy called Charles Bailey from Bloomberg, he has written something to help you out with this, to go through your history and find out where the bottlenecks are, where the large files are. So one way to use this is say, it's built up of very small binaries again, but it's not quite as big a problem as Git filter branch. So we're going to say, show me anything in history that is bigger than 5K, or 50K. Yes, 50K, sorry. Anything bigger than 50K. That will throw out a brief report that is almost no use at all to you. It contains the SHA, the latest version of that file, its size on disk, and then the average blob size. And that's what's kind of important, because you may have taken put a large file in there, but then replace it with a smaller file. You put a full PNG, 1200, 1800, and then you go, oh, so that should really be a thumbnail. Shrink it down, put it in. On disk, it looks big, looks small. In history, it's big. So you're interested in more of the historic size rather than the current size. Now, from that, you can pipe it into another command he added to get a little bit more useful information. This actually uses a lower-level Unix file command that gives you metadata about a file on disk. And we can see these are PNGs, and they're quite large. Then we can push this through to sort, the standard Unix tool, and we can basically say, sort, give me, sort these by size, average size on disk. We can do, possibly then we could do like give me through to head and say give me the top 10 disk usage or anything larger than this. And then for some reason, things break down at this time and it stops being pipeable. I don't quite know why. So we pipe it out to dump it to a file, and then we run a report on that file. So give me, what is actually going on under the hood here? And the answer is there are a couple of files in there called logo, and they are causing some issues. If you know anything about the Android world, these are probably the high-definition versions of logos for the high-resolution devices. So we probably want to do something about that. Again, we go back to our old friend BFG, and we convert those in. That will go through your history, completely rewrite your Git history, changing all those logos into LFS blob stores, separated out into pointers and stores. So that's a little practical thing. However, Git is about teamwork. This is all really moot if you're talking about a single person working on a single repository. What's interesting is when you're talking about lots of people working on different branches and trying to cooperate. Well, this is where it gets interesting. Binary files do not merge well. There are theoretically binary files that do, but if you know that your binary files are mergeable, you'd probably have come up with your own custom merge strategy. Generally speaking, if you do Git LFS files, they're probably not mergeable. PNGs, definitely not. JPEGs, even worse. So, what do we do about merge conflicts? How do we ensure that we're not stomping all over each other? Because the problem looks a little bit like this. Tim Peterson, interestingly, the original author of the old previous versions of this talk, has gone and re-rendered our little dancing elephant. Moved to high resolution, used a new server farm. It's really, really fast. 16 hours of work. Great. Meanwhile, Mel has been working away on that same video as well. Oops. We now have two people who have made changes to an unmergeable file. Who wins? Fist fights have occurred for less than this. Someone is going to be out of luck. We don't know who that is yet. Don't want to know. Now, this is where I segue a little bit into the future. And if I have some time at the end, I will talk a bit about some other future things coming down the line. But one thing that we'd really like in this world is locking. Everyone knows this film, right? You've all seen Breakdance, the movie, 80s classic? Oh, God, kids nowadays. No one teaches the classic anymore. Terrible movie. Don't go back and watch it. 30-year-old me thought it was great. 45-year-old me probably isn't going to enjoy it very much. Now, locking would be nice, but locking is the antithesis of the Git world. It's never had locking. It doesn't work in distributed file systems. However, we are talking more about centralized servers now, so maybe we want to start thinking about a possible locking strategy. We are now away from the standard Git model, we're into a modified Git model. Now, the simple, naive, and really subversion-oriented locking strategy here would be branch-based. We're not going to do that, but we'll explain why it's an issue. So we have a person on master, and they decide they're going to lock this baby elephant, and we're going to modify it. And we're going to make it pink. And we're going to give it a tattoo, as we did before. Great, we release our lock, and we're done. Sort of. The problem is all of these other versions are now out of date, but are still lockable. We've not really solved our merge problem. We've just solved it on a single branch, where people are working on other branches. Subversion wasn't too much of a problem because nobody used branches because no one could bloody merge the things. But in the Git world, we can merge, and we assume we're going to merge, but in this breaks. So this is lame. Can we come up with a better strategy? Well, this is where I said Atlassian's model had some slight improvements, and one of them was Steve Streeting, one of the guys who works for Atlassian, came up with the original Git LOBS idea, which proves that great minds do think alike. He came up with a different idea about this, and this is one of the things that is currently being merged into Git, the Git LFS. One of the things that he actually didn't do the work, he came up with the model and handed it off to a guy called Taylor Blau. And so I jumped back a bit there. Who did it as a summer of code. It's actually landed on master, but it is hopefully going to be in Git 1.3. We don't know yet. But this model looks a bit different, and it makes a bit more sense in the branching world. So what happens is somebody locks the file, same as did before. Fine. We make a modification to it, and then we release it. Now remember, this is all being requested from the centralized server, which has special knowledge about the state of the binary files. So next person goes they want to lock. That's going to fail. The reason being, you can only, for a given path, you can only lock the latest version of that file. So this means we have to somehow get the latest version before we can lock it. Well, there are a couple of ways you can do that. In this case, our person working on feature 1 has decided to rebase. They've rebased up, and now they have the latest version, and they can lock it and make modifications to it before unlocking it. Now, person on feature 0 tries to get a lock, gets refused, you are out of date. Somehow get up to this revision. Well, they've taken a slightly different path. They've decided to cherry pick it in. And now they can lock that file, modify it, and release the locks. So we've got this much simpler system. It's quite intuitive once you're aware of it, which is that a given file can only be locked globally across the entire repository, and only the latest version can be locked, which makes a certain amount of sense, I think. As I say, this is going into Git Master. It's currently in Git Master. We don't know if it's going to be fully ready for Git 1.3, but we hope so. The actual API, the command line, is actually pretty straightforward. It's almost exactly what you'd expect. You try to lock, you can unlock, and you can get a list of locks. Now, at this point, the strategy assumes that anyone can break the lock of anybody else. That rule is a matter for the server to decide. I would imagine that upcoming implementations, including Atlassian's, would include your ability to tune that, or certainly coming down the line. All of this really, though, is somewhat academic because it doesn't actually exist yet. And it also requires server support, so until we have server-level support, it's probably not going to be out for a while. So until then, here's another strategy. Try talking to your co-workers. At this point, the best strategy for it is to say, communicate and make sure that you're all on the same page, and then you make sure you're not going to stomp on each other. But hopefully better solutions are coming down the line. Okay, a few more practical issues. Let's talk a bit about tuning our system. As in, with most things, Git is actually quite tunable, and there are a lot of settings that you can set, and I'll show you why you might care about these. One thing is, if you do a Git LFS fetch or a pull, it will only pull down your current branch and the latest versions on your current branch. Now, most of the time, that's fine. The problem is, often, particularly say you're about to do a whole bunch of reviews on different branches or code reviews, you probably don't just want the latest version on the current branch, you probably want it on all related branches or recent branches. So there's a tuning command you can use, recent, and that will pull down the latest version on all branches you have checked out within the last 7 days, the latest commit on those that have been modified in the last 7 days. So it looks like this. So we'll pull down those. Now, of course, this is quite tunable. For starters, you can specify this globally. If you're quite close to your server, you have a fast connection, and you do a lot of reviews, you maybe just want to do this all the time. You can also be a bit more aggressive or less aggressive as you want. You can decide how many days back you want to be. Do you want to pull down more branches or less? You can specify a certain number of commits. So maybe not just the latest commit, maybe you want to fetch the last 3 commits on every branch that's been modified in the last 7 days. And you can go further and say, I want to pull down all of this for all references, all branches, even if haven't got them currently checked out. Now, obviously, if you're in a large team and a lot of branches, that's going to get noisy pretty quickly. That's really a question up to you. This is why it's called tuning. It's not a global setting. Obviously, there is something that you intuitively would understand is that there's the opposite, which is prune, which will prune back any old versions that are on disk and save you some disk space. So basically, if you don't have a reference to it anymore, or there's a newer reference, that uses the same 7 days, so it's 7 days plus 3, so it will be 10 days by default if the setting is free. The other cool thing that probably should be on by default is you can say before you prune, make sure that the upstream server has a copy of this object. It should do, but it's good to check. Of course, that will go off to the main server and check. At the other end of things, we have the possibility, well, I don't want to pull down everybody's changes. I'm only interested in certain parts of it. You've got a game design team. Some of them might be working on audio, some might be working on video, and some might be working on code. So we want the ability to tune a little bit more there as well. So we have the ability to exclude certain paths, fairly standard type of syntax. And at the other end, we want to say we can include, do everything except a certain batch. So the first one, if you don't run a unit test, you don't want to pull down all the audio and graphics assets, so it's part of your continuous integration pipeline. You probably don't want to pull down all the images just so you can run a bunch of unit tests that have nothing to do with images. On the other hand, maybe if you're an audio engineer, you might want to pull down just the audio assets so you can be very specific there. This kind of encourages you to maybe divide your repository up into certain logical groups. Again, this is globally settable. So you can tune this either at the per repository level or at a global level, depending on what's important to you. Now, in terms of practical issues, another one is okay, great, we've got this theoretical storage server. What are our options currently for this? Well, there are a couple out there. Obviously, GitHub are working on this as well. But Atlassian is also working on it. In particular, we have Bitbucket. Currently server-side only. Cloud, we are actively working on that, and hopefully should be coming quite soon. Now, there is a way of overriding this. So, for instance, JFrog's Artifactory is working with Git LFS support as well. If for some reason you prefer to use Artifactory, maybe you have existing auditing tools in place, or some policy says you only use Artifactory, then you can, by setting your LFS config, you can basically override where your repository is. However, there are certain advantages to having your Git and your LFS storage on the same server and making both aware of each other. Bitbucket server now has LFS support, and it's really just a question of enabling it. So you have a Bitbucket server, formerly Stash. That is available for you right now if you have the latest versions of that. And that gives you a certain number of advantages. The obvious one being, these files are now stored in Git as text metadata. If you make a modification to a binary file, what appears inside the server is just a modified metadata file. Not super useful. What we would prefer is to have something more like this. So, LFS-aware server, particularly at the front end, will give you a lot of advantages in terms of usability. There are a few options out there. Obviously, I would like you to buy Bitbucket, please. Bitbucket Cloud is coming soon, and you will hopefully be able to use it. I can't tell you when because I don't actually know. I am using it internally, though, so it is on the way. The other question might be, in terms of practical issues, is GUI tools, IDEs. Maybe you're not a command line person. Maybe you need to integrate with your existing tools. Does Git LFS work with your tools? The answer is mostly. In particular, any system that forks out and uses the Git binaries on disk will actually probably just work once you've done your Git LFS install that we did down here at the start. JetBrains in particular, there's no official statement about this, but we've poked around with this. Seems to work fine. I think it just forks out the Git binaries. eGit for Eclipse does actually work with the latest versions. The reason for the latest versions is that it uses Git JGit under the hood, and that you have to add support for certain of these hooks, like smudge, clean, and pre-push. Older versions didn't support that, newer versions do, so the latest versions of eGit use that, and it just works. Same with NetBeans, it seems to just fork out into the Git binary, so that's cool. What doesn't work, boo, is Xcode. so someone's an Apple developer here. Do you know why? They've forked Git. They've got their own copy of Git that they use inside Xcode, and it is not up to date. Also, happy birthday to rsync. It is now 10 years old in OS X. Get your head around that. So, bit of a problem there. However, you can still revert to the command line tools. They will work, particularly if you're pulling them out from Brew. Now, there's SourceTree, which is an Atlassian product again. This has first-class support for Git LFS, including a bunch of useful things like doing on-disk verifications and so on, and will check a repository for integrity. The reason for this is why it's such first class, obviously, other than it's Atlassian, is the guy who came up with Git Lob and is now one of the most active contributors to Git LFS, and the more interesting parts of it is Steve Streeting, who also wrote the original SourceTree. So this is pretty much a summary of where we are with Git LFS, but more stuff is coming down the line. There's a lot more information out there if you are interested. Here's a couple of links that are of interest. And also, there's a couple of other people you might want to follow. Cannon Boy, a.k.a. Tim Peterson, who did the good part of this talk. All of the unfunny jokes are mine. And Durden is none other than Nicola Paolucci, sitting down in the front here. He is also giving a talk tomorrow at 11:30, I believe, on Git as well. I recommend seeing that. He's always good. It's very, very big with the hands. So now, this is pretty much the state of play. I have 5 minutes left because when I originally rehearsed this talk, I thought it was 40 minutes and not 50 minutes. So I'm going to talk slightly longer about cool things. What's coming down the line? At this moment, if you actually, this is cool. I've put a link up here, but if you go to the Git LFS repository, it's in GitHub, and go to Docs, Experiments, or Proposals, I think. Under there is a bunch of markdown files, which is a current list of actively worked on proposals, some of which are advanced. Git locking API and the Git locking proposal is in there. There's one for NTLM, I hope it's NTLM, which is the Windows authentication as necessary. But there's also one in there for what's called pluggable backends. There is a pluggable transfer system. The idea behind this is that we would like, in the future, to have more options in terms of how the binary level talking back to the LFS server is. This currently is fairly naive and it's HTTPS only. We want something a little bit more advanced. In particular, one of the advantages that Git Lob had over Git LFS at the time when we decided to merge the two was it had chunking support and it has resumable downloads. These do not currently exist, but right now, Steve Streeting is actually working on a back-end that will give you pluggable systems. And that allows a lot of really interesting things. One, chunking and resumes will probably be the next thing that he works on. Don't quote me on that, for God's sake. but that is definitely high on the list of what things that people want, and he's enabling that. The other thing is a lot of really other cool things become possible. Binary diffs would be really nice. One of the things that Git Lob had that Git LFS does not yet have and requires these pluggable backends is the ability to not transfer the whole file every time, to take binary diffs and only transfer the deltas across and resume and resolve them at the other end. This is going to be used something that's actually a protocol has an RFC behind it called VC diff, which is a binary diffing system for the web. So that will be a really useful plugin to have as well on there. There's a lot of other really cool things you can plug in, maybe not HTTPS, maybe we'd like to do something else. One really cool out there thing is a project called IPFS, which essentially is Git as a storage model for interplanetary file systems, a way of replacing network protocols with storage protocols and then having an immutable web over time. It actually looks an awful lot like Git and actually uses the Merkle trees that I talked about. So having that as a backend might be good. Maybe you have a shared storage system across your entire company. Plugging that in should be possible as well. So this is still the early days of Git LFS. It's usable right now. We are rolling it out in Atlassian to our Git-related products, and you can go out and use it on Bitbucket Server now, and hopefully very soon on Bitbucket Cloud. It does solve a bunch of problems with the caveat that it slightly alters the Git model, as hopefully you now understand. So that is the sort of past, present, and future of Git and Git LFS. Hopefully this has been useful. Thank you for your time.